Welcome back. In this video, I'm going to solve exercises 1 to 3 of chapter 3 about the uniform boundedness principle. In the first exercise, you are asked to prove corollary 3.2, corollary of the uniform boundedness principle, which states the following. If a subset B of a Banach space satisfies the property that its images under any linear bounded map from E to R is bounded in R, then B is bounded. So, why this is useful? Because the image of B under any linear bounded map is a subset of R, right? Linear functions here, so an element in E star. So it's easier to work with subsets of R than with subsets of a Banach space, okay? So to prove that a subset is bounded, then we look at its images under all linear continuous functionals from E to R. Okay, so in order to apply the uniform boundedness principle, we introduce a family of operators. So for x in B and f in the dual of E, we set t sub x of f to be just f of x. So, of course, it's linear and bounded from E star into R. It happens that t is linear in x, but this is not the point. It's linear in f, and of course continuous in f, as you may check, because the absolute value is less than the norm of f times the norm of x. Okay, so what does it mean that f of b is bounded? If I pick one f, it means that f of b is contained in some closed interval. Let us call it minus capital M, capital M. So it's a ball, let us say, of center 0 and radius m. Okay, so if you call this quantity capital M, then this is just equivalent to saying that the supremum of Tx of f. Here I'm taking the absolute value because this is just the norm on R. When I say nothing, then the usual norm on R is just the absolute value. Okay? So the boundedness of f of b means exactly that this quantity Tx of f is less or equal than a certain constant, capital M of x, because it depends on capital M of f. Okay. Now, since E star is complete, we can apply the Banach-Steinhaus theorem, which implies a more precise upper bound. Okay, so this is actually a pointwise bound, so it depends on f. But the conclusion of the Banach-Steinhaus is independent on f. Okay, so this is, if you like, I can call this quantity capital M sub f, and this quantity now is capital M. Okay, so what does this mean? It means that Tx of f, an absolute value, this is the norm in R, is less than this constant here, capital M, times the norm of f. Yeah. And so if f is in the unit ball of E star, then this is less than M, right? So this means that f of x in absolute value is less than a constant M for every x in B and for every f in the closed unit ball of E star. So if I take the supremum of this quantity over the unit ball of E star, I get what? By a corollary of the Hahn-Banach theorem, this is just the norm of x. So I get norm of x is less than M for every x in B. Okay? So this means that B is contained in the closed ball of center 0 and radius M. Okay, so this means that B is bounded. Okay, now first remark, the operator T sub x is just what we call Jx, where J is the linear injection from E to the bidual of E. Okay, it happens here that Tx is linear in x. Okay, but I didn't use that. And second remark, we don't need to assume that E is complete. We only use the completeness of E star, and E star is always complete, even if E is not complete. And of course, R is always complete. Okay. The next result is a dual statement of this result. So here we are considering a subset B star of the dual of a Banach space, whose image under Jx, so this is just Jx of B, if you like, okay, is bounded for every x. So we have to conclude that B star is bounded. So this is useful because, once again, it's easier to work with subsets of R than to work with subsets of a dual of a Banach space. Here we need the completeness of E. Okay, so this is just Jx of B. Okay, so here for every f in B star and for every x in E, we set capital S of f of x is just f of x. So it's the same operator actually, but it works on between different. It's not the same operator because this is an operator from E to R. Okay, so for each f we get a map from E to R. Okay, it's the same formula if you like, but here I interchange the roles of f and x. Okay, so here again, so S sub f is just f, right? But I use this notation just to apply more easily the Banach-Steinhaus theorem. So SF is just f. Okay. So what does it mean that Bx is bounded or Jx of B is bounded? It precisely means that when I fix x, there exists a constant. So SF of B, if you like, or if you write the condition that this is bounded, so call this capital M sub x actually. Okay, so if this is bounded, it's contained in some interval minus capital M sub x, capital M sub x. Okay, where the bound depends on x. Okay, so this is pointwise boundedness, if you like. So you denote this by capital M sub x. Okay, so this quantity is finite. And since E is complete, we can apply the Banach-Steinhaus theorem, which gives me a better, much better estimate of bound. So it tells me that the supremum of the norm of SF is finite. So, and this is equivalent to saying that the norm of Sx of f, which is just the absolute value because the target spaces are. So this quantity is less than this quantity that I call M times the norm of x. Okay, so it's completely parallel, if you like. But now I don't need to use the Hahn-Banach theorem. I just use the definition. So I have f of x, which is just Sf of x, is less than this constant capital M for every x in the closed unit ball and for every f in the set that I'm interested in, B star. So when I take the supremum over x this time, I get what? I get by the definition the norm, the operator norm of f. Okay, so this is just the definition, not the Hahn-Banach theorem. So I take the supremum over x. So the norm in E star of f is less than a constant m. So this means that B star is contained in the ball of center 0 and radius m. And this means that B star is bounded. Okay, so this concludes the second exercise. Last exercise, we asked it several times in the exams actually. So we have two Banach spaces, E and F, and you have a sequence of linear bounded operators from E to F that converges pointwise, okay? Not necessarily uniform, it converges point. So Tn, for every x in E, Tn of x converges to some limit T sub x. Okay, so we have to show that if xn converges to some point A in E, then its image under Tn, so Tn of xn converges to Ta. Okay? This is not true for any sequence. You can give counterexamples actually. And if you use the counterexamples that we encountered an example in chapter 1 actually, where this is true, but this is not true. Okay, but here we have linear bounded, a sequence of linear bound maps, so it's very specific. Okay, so the key is to use the triangle inequality. So estimate the distance between Tnxn and Ta. Okay, so we add and subtract Tna. So this norm is less than Tnxn minus Tna in norm plus the norm of Tna minus Ta. Now, since Tn is linear and bounded, so I can factor by Tn. So this is just by linearity. This is Tn of xn minus A. So by the operator norm, so this is less than the operator norm of Tn times the norm of xn minus A. This is the fundamental inequality of all linear bounded maps. And I leave this term as it is. This term tends to 0 because by assumption. Tn of x converges to a limit tx for every x. So in particular, Tn of a converges to Ta. So this goes to 0. Now what about that? Xn converges to a. So this term converges to 0. But what about this term? It's possible, in general, if this term tends to 0, this term, if it could tend to plus infinity. In this case, the product does not tend to 0. Okay, this is why you have to make sure that this is bounded. But this is indeed the case. Why? By the uniform boundedness principle, by the corollary, actually, of the uniform boundedness principle, corollary 3.1. It tells me that if this is true, then the sequence of norms is bounded. So this term tends to 0, and therefore this upper bound tends to 0, and so this tends to 0. Okay, so this is a very elementary and standard argument in analysis. Okay, so this concludes exercise 3 and this short video. So thank you for your attention, and see you next time.